Usually, like when we talk about a medical diagnosis, there's this expectation of precision, you know?
Oh, absolutely. Yeah.
It's almost like engineering. You break your arm, the x-ray shows that jagged white line, and the doctor just points at it and says, you know, there it is.
Right. It's totally binary. It's
Mhm.
either broken or it's not broken. And we naturally gravitate toward that kind of certainty.
Yeah, we really do.
We like things to be visible, to be neatly categorized and just easily measured.
But then you step into the world of human intelligence, right? And specifically how we learn. And suddenly that x-ray machine is just, I mean, it's completely useless.
Completely.
We're looking at a cognitive landscape that is incredibly murky. You can't just take an x-ray of a 10-year-old's brain to see if they, understand fractions.
No, you can't. It is the absolute definition of diagnostic muddy waters. Measuring understanding requires indirect observation, which is, by its very nature, inherently messy.
And that is exactly what we are wading into today. For this deep dive, we are looking at a massive, incredibly dense stack of review documents.
Very dense, yeah.
Yeah, these were designed for the Philippine licensure examination for teachers, specifically the mathematics portion.
Which sounds super intimidating.
It does. These are the actual texts that future educators use to prepare for their exams. But if you're listening right now and thinking, oh, great, they're going to read me a math textbook, do not worry.
No, we're definitely not doing that. The math itself is really just the surface layer here.
Exactly. Our mission for this deep dive is to extract the hidden narrative within these pages. We aren't just going to look at the raw rules of algebra or, like, geometry.
Right.
We are going to decode the fascinating psychology of how the human brain actually learns a complex system and the scientific methods we use to measure that invisible intelligence.
Okay, let's unpack this.
So to really understand how to teach math, or even how anyone learns it, we first have to look at the anatomy of what is actually being taught.
Great, the structure of it.
Exactly. Mathematics, at its core, isn't just a collection of numbers. It's really a system for translating reality into symbols. Which is wild because I always struggled with word problems in school.
Most people do, honestly.
Yeah. But the text frames them as literal translation exercises. It shifts the perspective entirely. Take this classic work problem from the source.
Oh, the cleaning one.
Yeah, so Jamie can clean a house in 6 hours. Christine can do it in 5 hours. How long does it take them if they work together?
Right.
You don't just guess. You translate the English sentence into a formula.
You're taking a messy, real-world human scenario, two people scrubbing floors, and distilling it into a completely frictionless equation.
Right, getting rid of the mess.
Exactly. Jamie's rate becomes the fraction 1/6. Christine's rate becomes 1/5. You set them up to equal 1 over the total time.
Wow.
You literally strip away the brooms and the soap, and you are left with pure logic.
So algebra is basically a foreign language translation class.
That's a great way to put it, yeah.
Like the phrase decreased by translates directly to a subtraction symbol. Ratio translates to a division line.
Yeah.
We're just turning English grammar into mathematical grammar.
What's fascinating here is how these simple, seemingly isolated translation rules build the foundation for incredibly complex predictive systems.
Like what?
Well, once you understand that an equation is just a sentence, you can start manipulating reality without having to, physically experience it.
Okay, I'm tracking.
The source material spends a lot of time on something called the fundamental counting principle.
Oh, yeah. Let's break that down because the name itself sounds really intimidating. How does it actually work?
It's surprisingly intuitive, actually. Let's say you have 3 different shirts and 4 different pairs of pants.
Okay, 3 shirts, 4 pants.
Right. If you want to know how many unique outfit combinations you can make, you could physically lay them all out on your bed and count them one by one.
Which would take forever.
Exactly. But the fundamental counting principle gives you a shortcut through the language of arithmetic. You just multiply 3 by 4 to get 12.
Just like that.
Just like that. It represents the underlying mechanism of sequences and combinations. It allows you to predict future outcomes or even scale up to thousands of variables without doing all that manual labor.
And speaking of shortcuts, there is a mental math technique in the text for multiplying 2-digit numbers that completely caught me off guard.
Oh, I love this part.
It's so cool, but it only works under a very specific set of conditions, like the rightmost digits have to sum up to 10, and the left digits have to be identical.
Yeah, it's a great example of pattern recognition in arithmetic.
Yeah.
Walk me through the mechanics of it.
Okay, so the example they give is 36 times 34. Let me actually do this live.
Go for it.
So the right digits are 6 and 4. Those add up to 10.
All right.
The left digits are both 3. So the rule says I multiply the right digits first. So 6 times 4 is 24. Okay, I have that piece. What do I do with the threes?
Okay, so you take that left digit, the 3, and you multiply it by the next consecutive number in the counting sequence.
Oh, which would be 4.
Exactly.
So 3 times 4 is 12, and
Right,
then I
got it.
just put them together, like 12 and 24. So 12, 24.
That's it. 36 times 34 is 12,224.
That is wild. It feels like a magic trick.
It really does. But it is actually just an exploitation of base 10 algebra. The distributive property is working in the background, factoring out the 10s and the 1s.
Right.
But because the conditions are perfectly set up, the middle terms just cancel out in a way that lets you skip all the messy middle steps.
That makes so much sense. We are using the rules of the language to find a faster route to the truth.
Precisely. Now, if algebra is the language of mathematics, we can think of geometry as the physical architecture of those ideas.
Okay, moving from sentences to structures.
Exactly. Algebra gives us the sentences, but geometry gives us the actual space where those sentences live.
See, here's where my brain started to hurt a bit.
Yeah, it gets abstract.
Very. The sources map out how the entire mathematical system of geometry is built on what they call undefined terms.
Right. Point, line, and plane.
Yes. Point, line, and plane. These are the building blocks for every single theorem and postulate that follows.
They are the absolute bedrock of spatial reasoning.
But I have to push back on this concept because it feels incredibly ironic to me.
How so?
Well, you have geometry, right? Which is famous for being a perfectly rigorous, painstakingly logical system. You have to prove every single theorem step by step using cold, hard facts.
Right. You can't just guess.
Exactly. Yet the entire foundation of the house is built on concepts that the system outright refuses to formally define.
It is pretty funny when you think about it.
I mean, a point has no dimension. A line has straightness. That is just like assume. It's basically a mathematical foundation of just trust me.
It is a brilliant paradox, honestly. But let's look at why mathematicians were forced to do that. Think of it like a dictionary problem.
A dictionary problem.
Yeah. If you try to define a word, you have to use other words.
Right?
And then you have to look up the definitions of those words, which use even more words.
Hmm.
In a formal logical system, if you try to define a point, you fall into an infinite regress. You literally never reach the bottom.
You just keep digging forever.
Exactly. So mathematicians had to collectively agree to just stop digging. Accepting undefined terms is an exercise in what the text calls logical mathematical intelligence.
Okay, so it's a shared understanding.
Exactly. We all share a basic human intuition of what a location in space is, or what a flat surface is. We agree on the invisible, undefined foundation so that we can build a highly visible, highly rigorous house on top of it.
And what a house it is. I mean, the text dives into trigonometry applications, showing how we use that invisible architecture to measure the real physical world.
That's the best part.
There's this specific example of using the tangent function to measure the angle of depression from a 43-foot tower just to find a distance on the ground.
That's where the abstraction really proves its worth in reality.
Can you explain how that actually works for someone who maybe hasn't taken trig in 20 years?
Sure.
How does an angle help me measure a distance on the ground?
Okay, imagine you are standing at the top of that 43-foot tower.
I'm up there.
You look straight out horizontally, perfectly parallel to the ground. Then you tilt your eyes down to look at an object on the ground.
Okay.
That downward tilt is your angle of depression. Now, because you know the exact height of your tower, and you know the exact angle your eyes tilted, you suddenly have two pieces of an invisible right triangle.
Oh, I see it.
The tangent function is essentially just a pre-calculated reference sheet of ratios for every possible angle. It tells you exactly how the height relates to the base.
So I don't have to climb down the tower and drag a giant tape measure across the dirt.
Never. The math does the walking for you.
That is so cool. So we've built this invisible, perfect world using algebra and geometry. But how do we bridge the gap between that abstract perfection and a messy physical student?
That is the million-dollar question in education.
The psychology section of these review notes tackles this head-on. They talk about an educational psychologist named Jerome Bruner and his concept of knowledge representation.
Right, a very influential theory.
He argues that a teacher has to move sequentially through a learner's brain.
You cannot just jump straight to the abstract equation on the chalkboard.
Exactly, because that is not how human beings evolve to understand their environment. Bruner says you have to start in the physical world with what he calls the inactive stage.
So physical blocks.
Yes, The student has to literally hold 3 blocks and take one away.
It anchors the logic in tactile reality. You
Yeah.
can feel it.
Then you graduate to the iconic stage. You draw a picture of the blocks on paper.
Moving one step away from the physical.
Right. And only when that is mastered do you move to the symbolic stage, which is the actual numbers and minus signs. The text makes it very clear that jumping straight to symbols is exactly why so many students fail.
And this connects deeply to Howard Gardner's theory of multiple intelligences, which the text also heavily features.
Oh, right.
Traditional schooling often heavily favors linguistic and logical mathematical intelligences, but not everyone processes information best through pure logic.
Some people need to touch things.
Exactly. Some learners rely heavily on spatial reasoning or bodily kinesthetic engagement. This realization leads to the pedagogical concept of situated learning.
There is a quote in the source material about situated learning that I think perfectly captures this.
Was it?
A teacher says, "If it is billiard that brings students out of the classroom, let us bring it into the classroom. Perhaps I can use it to teach math."
It's a wonderful philosophy.
Yeah.
It asserts that knowledge really needs an authentic, real-world context to stick. You are mapping the physics of the billiard balls directly to the geometry of angles.
Here's where it gets really interesting for me, though. I have to play devil's advocate for a second.
Okay, let's hear it.
Does everything have to be a highly curated, real-world game? Like, the text contrasts this kind of authentic assessment with traditional drill and practice?
It does.
Authentic assessment is when a teacher has students construct their own word problems, swap them with a partner, and solve them together. It's highly interactive.
Very engaging.
But surely there is still a place for rote memorization. I mean, do we just throw out the flashcards and drill software entirely?
If we connect this to the bigger picture, it's not an either situation. It's really a progression of cognitive load.
Cognitive load.
Yeah, drill and practice serve a vital mechanical function. They build automaticity. Think about learning to read.
Yeah.
You cannot appreciate the metaphor in a poem if you were still actively sounding out every single syllable.
Oh, that makes sense. You'd be exhausted.
Right. Drills give you the math vocabulary so that your working memory isn't overwhelmed.
So the drills give you the tools, but the billiards teach you how to actually play the game.
Yes, beautifully said. Situated learning, that authentic context, the billiards, the social collaboration of swapping word problems, that is what creates lasting comprehension and problem-solving skills. You really need both to function at a high level.
Okay, so a teacher uses the blocks, the billiards, and the drills to build the knowledge. But education isn't just about teaching, right? It's about verifying.
Yeah.
Exactly. How do we scientifically prove that the learner actually absorbed the physical reality and the abstract symbol? That brings us to the final section of the sources, statistics and measurement.
Because to measure the mind, you really have to look at distributions.
The text breaks down the two main things we measure: central tendency and variability. Central tendency is your mean, median, and mode. It's the average stuff we hear about literally all the time.
Everyday stats.
But the text argues that variability, specifically the standard deviation, tells the real story.
The standard deviation is such a vastly underappreciated tool. It tells you how compressed or expanded the distribution of scores really is. Think of a highway where the average speed is 65 miles per hour.
Sounds like a pretty safe, normal highway.
Right, but what if I told you the standard deviation was huge? Like half the cars are going 30 miles per hour and the other half are going 100 miles per hour.
Oh, wow. That sounds terrifying.
The average is still 65, but the actual reality on the ground is chaotic and dangerous. A large standard deviation means the individual experiences are wildly scattered from the mean.
There is a specific story in the text that perfectly illustrates why looking at just the average grade is a terrible way to judge someone's intelligence. It's the story of a student named James Mark.
Yes. The Z-score example. This is a crucial concept.
Let's walk through this slowly because the numbers really paint a picture. James Mark gets his report card. He got a 95 in math analysis and an 80 in natural science.
Okay, 95 and 80.
Now, if a parent just looks at those raw numbers, they'd say, "Great job in math, James Mark, and 80 in science is okay, but you clearly need to study a bit harder."
A totally normal reaction.
But the text introduces the Z-score, which measures exactly how many standard deviations a specific score is above or below the class mean.
It contextualizes the individual against the environment. A raw score exists in a vacuum. A Z-score tells you where you actually stand in the room.
Right, so in math, the class average was an 88, But the standard deviation was a very wide 10 points.
Meaning people were scoring all over the place.
Exactly. So James Mark's 95 gives him a positive z-score of 0.70. He is comfortably above average, but not an extreme outlier.
Makes sense.
Now let's look at science. He got an 80. The class average was an 85.
So he's slightly below the average.
But wait, the standard deviation was an incredibly tight 5 points. Almost everyone in the room scored between 80 and 90.
Which completely shifts the narrative.
Because the standard deviation was so tight, James Mark's score of 80 gives him a z-score of -1.
Meaning he performed a full standard deviation below the average. Relative to his peers, his performance in science was actually quite poor. Much worse than the raw number 80 implies. He is essentially at the bottom of the pack.
So what does this all mean? For you listening right now, the takeaway extends far beyond a classroom. When you read a survey or when you look at performance data at your job, do not just accept the average.
You have to ask for the standard deviation.
Yes. A massive standard deviation means the real-world experiences of those people are wildly scattered. An average is a blanket that hides the extremes.
This raises an important question about how we judge success and failure. And not just of the students, but of the systems themselves. The sources dive into how tests can fundamentally fail the learner.
Yeah, they discuss the concept of skewness on a test distribution.
This is fascinating.
This part was entirely counterintuitive to me. If a teacher gives a test and the results form a positively skewed distribution, it sounds like a good thing, right? I mean, the word positive is right there.
It does sound encouraging,
Yeah.
but visually, it actually represents a failure. Think of the classic bell curve.
The big hump in the middle.
Right. In a normal distribution, the massive hump of the bell is right in the middle. But in a positively skewed distribution, the tail of the curve stretches out far to the right toward the high positive scores.
But the tail is the skinny part. That means only a few kids got those high scores.
Exactly. If the tail is stretching right, it means the bulk of the bell, the massive hump where the majority of the students actually reside, is clustered on the far left side at the bottom of the grading scale.
It means most of the students bombed the test.
Yep, the test was actually way too difficult.
Wow.
A positively skewed test evaluates the test maker's failures just as much as the test takers. It basically tells the teacher, you either didn't lay down the physical blocks correctly or you asked questions that didn't align with the situated learning.
Which is exactly why the text spends so much time analyzing rubrics. How do we fairly judge the work? They compare holistic rubrics to analytic rubrics.
Two very different approaches.
Very different. A holistic rubric gives a quick overall score. It's like taking a bite of a cake and saying, this is a C- cake.
It's fast for the teacher, but it lacks any usable detail.
An analytic rubric, on the other hand, scores every single component independently. The texture gets a score, the icing gets a score, the bake time gets a score.
Right. It takes the teacher vastly more time to grade, but it actually tells the student where they went wrong.
Instead of just hearing, this cake is a C-, the student learns, your icing is perfect, but you use salt instead of sugar in the batter.
The analytic rubric provides actionable feedback. And notice how that loops right back to Bruner's concept of sequential learning.
Oh, true.
An analytic rubric guides the learner back to the specific physical reality or the specific abstract symbol they need to fix. It makes the invisible process of learning visible again.
We have covered some serious ground today.
We really have.
We started by looking at algebra not as a rigid set of math problems, but as a dynamic language translation exercise. We explored geometry's perfectly rigorous architecture and how it is built entirely on the undefined trust of points and lines.
And then we examined the psychology of bringing that architecture into the human mind, moving from physical blocks to pictures to abstract symbols, and the vital importance of anchoring that logic in situated real-world learning.
And finally, we looked at the statistical science of actually measuring that learning. We proved why a z-score tells a much truer story than a raw grade, and why a positively skewed test is actually a teacher's nightmare.
It's a really comprehensive look at the entire life cycle of knowledge, from its raw, logical structure to its human acquisition, to its scientific measurement.
And whether you are prepping for a teacher's licensure exam or not, understanding the mechanics of this life cycle makes you a vastly better self-educator.
Absolutely.
When you are trying to learn a new complex skill at work or at home, remember Bruner's blocks. Don't start with the most abstract symbols, start with the physical reality. And when you are consuming data in your daily life, remember James Mark.
Look for the standard deviation.
Yes. Don't let the averages fool you.
Knowledge is most valuable when you understand the mechanisms behind it, allowing you to apply it to how you interact with the world around you.
Which brings us back to that X-ray machine we talked about at the very beginning. We naturally like clear binary answers, broken or not broken, smart or not smart.
But human intelligence doesn't work like that.
No, it doesn't. Human intelligence and the way we absorb the universe is beautifully murky. And I want to leave you with a thought to mull over today. If statistical concepts like skewness can perfectly reveal when a test is fundamentally flawed and failing its students, how much hidden brilliance and raw talent in the real world is completely missed every single day just because society is measuring it with the wrong rubric.